signal analysis using deep learning techniques. Our paper is titled Advancement in Seismic Data Collection and Analysis through Machine Learning. I'm Malay, Phadke, and along with me I have my professor and mentor Dr. Sujata Kulkarni and Dr. Ashwini Sawant and my peers Neel, Patel and Patil. Our paper ID is 39590.
This presentation will cover the creation of our proposed and hybrid datasets, an explanation of seed data, the architecture of our deep neural network model, and a detailed interpretation of the performance metrics we've used. The outline for the presentation is as shown. First, we'll start with the introduction, then research contribution, methods and algorithms that we used, then we'll discuss our results. Further, we have conclusion and the references that we've used. Our study primarily focuses on advancing seismic data collection and analysis using deep learning techniques to improve earthquake detection. Earthquakes caused by a sudden release of elastic energy stored in geological faults generate seismic waves that travel through the Earth's crust. Among these, the primary wave, P wave, arrives first and displaces the particles in the direction of propagation, while the secondary wave follows, moving the particles perpendicular to the wave's direction. Accurate detection of these seismic waves is crucial for earthquake warning systems. However, managing large volumes of high frequency data recorded by seismic stations poses significant challenges. The objective of our research is to develop a robust deep learning model that can effectively distinguish between seismic and non-seismic signals, thus enhancing the earthquake detection accuracy and minimizing false alarms. By integrating techniques such as principal component analysis and hybrid deep learning models like LSTM and DNN, our study aims to address these challenges and improve the reliability of seismic monitoring systems. Now let's start with the proposed workflow, which outlines the step-by-step process used to develop our seismic signal analysis model. Input dataset, we begin with data collection, and the dataset contains both earthquake and non-earthquake signals. It includes raw seismic data, which is the foundation for our analysis. Then we have pre-processing, which involves data cleaning. Data cleaning is removing the noise and relevant information. This ensures that the signals used in the analysis are of high quality and free from distortions that could affect the model's performance. Then we have slicing and creation of the final CSV format dataset. This will be elaborated more in the further slides. After that, we have feature extraction. We extract prominent features such as amplitude, frequency. These features are crucial for distinguishing between seismic and non-seismic signals. After that, we have our model implementation, model training. The extracted features are then used to train a deep learning model. This training helps the model to recognize patterns and make accurate predictions based on the input data. And finally, we have our model evaluation. We analyze the performance of a trained models to ensure that it meets the standards of accuracy and reliability. The output of the whole process is an optimal deep learning model capable of accurately identifying seismic events. Further, we have feature extraction and analysis using the deep learning model. The feature extraction, the seismic signals are divided into 15-second intervals, and from these intervals we extract key features such as amplitude, frequency, time. We also calculate additional metrics like interquartile range, cumulative absolute velocity, and zero crossing. These features are essential to build a robust dataset that captures the critical aspects of seismic activity. Then further, we have dimensionality reduction. Given the large number of our features, we apply principal component analysis, that is PCA, to reduce the dimensionality of the dataset. PCA helps us retain the most important information while minimizing computational complexity. This step is vital for efficient processing and ensures that our models are not overwhelmed by too many variables. The reduced feature vector that we get from this is then set to fed into our deep learning model. By focusing on the most relevant features, we enhance the model's ability to accurately detect and classify seismic events. The final output from this process is a set of highly correlated features that are used for further analysis and training. We move on to our DNN architecture. We choose the DNN model for its ability to handle complex patterns in data. DNNs are particularly well suited for tasks with nonlinear relationships, which is common in seismic data. Our DNN model consists of multiple hidden layers, 5 hidden layers. The hidden layers process the features to identify patterns indicative of seismic events, capturing different levels of abstraction in the data. It also contains 2 dropout layers to prevent overfitting. The last layer contains a single neuron with the sigmoid activation function to perform binary classification into seismic and non-seismic events. Similarly, our LSTM DNN layer has 3 LSTM layers followed by DNN layers and the same last layer as our DNN model. Further, our model was trained on both proposed and hybrid datasets. I'll explain further what they mean, allowing it to learn from a diverse set of seismic conditions. Despite its simplicity compared to more complex models like LSTM, DNN achieved similar, if not better, performance with lower computational complexity. Before we dive into the dataset itself, I would like to explain what seed data exactly is. That is the standard for exchange of earthquake data. It is a data format intended primarily for the archival and exchange of seismological time series data and related metadata. SEED is designed for archival rather than processing, so most use cases like ours should use a different data format, that is like CSV. In seismology, seed data refers to the initial set of raw time series data captured by seismic sensors. This includes continuous recordings of ground motion representing both seismic events and non-seismic events, that is noise. Alongside the raw waveforms, seed data includes essential metadata such as timestamps, sensor locations, sensor characteristics, and event details like magnitude and epicenter. This metadata provides context and allows for accurate analysis. Seed data forms the foundation for creating larger, more refined datasets and undergoes processing steps, ultimately resulting in structured datasets fit for deep learning applications. The information that we've gathered is from a university in Maharashtra, India. This information is gathered from stations spread out in several locations. We use a broadband seismological signal sensor that collects data at a rate of 100 samples per second and has a sensitivity of 2000 volts per meter per second. The normal cycle lasts about 120 seconds. This signal used in this study has a total duration of 5 hours and was broken down into 1 hour segments sampled at 100 Hz. Two particular seismic events are noted by the Seismological Institute, one of magnitude 3.6 at 2:47 am and another of magnitude 2.8 at 2:38 am, as shown in the figure. Further, moving on to our creation of proposed and hybrid datasets. The proposed dataset was created by capturing raw seismic signals from sensors in various regions. These sensors recorded continuous seismic activity, including both seismic events and non-seismic noise. The raw data underwent pre-processing to remove noise and irrelevant information. This step is crucial as the seismic data often contains significant amount of noise that can obscure seismic signals. Further key features such as amplitude, frequency, and time were extracted from the data. These features are essential for understanding seismic activity and training our deep learning model. The proposed dataset was finally organized into the CSV format, resulting in a comprehensive dataset of 13,038 samples and 16 features ready for analysis. To enhance the robustness of our analysis, we further created a hybrid dataset. The hybrid dataset was developed by combining samples from the proposed dataset with additional data from sensors in regions including Port Blair, Shillong, Lakshadweep, and Kabul. This resulted in a larger, more diverse dataset containing 18,548 samples with same 16 key features. The diversity of the hybrid dataset helps the model generalize across different seismic conditions. Further, the figure in the slide shows our final converted CSV data file with the features that we've extracted and a column called class, which divides it into seismic and non-seismic events. Moving on to evaluate the effectiveness of our models, we use several key metrics. I'll explain the performance metrics that we have used. First, we have accuracy, the proportion of correct predictions out of all predictions, indicating the overall model performance. Precision, ratio of true positives to all predicted positives, showing how often models' positive predictions are correct. We have recall, the ratio of true positives to all actual positives, measuring models' ability to detect actual seismic events. F1 score, that is the harmonic mean of precision and recall, balancing both aspects of model's performance. And then we have AUC, that is area under the curve. It measures the model's ability to distinguish between classes, with higher AUC indicating better performance. The values of these performance metrics are showed in table 2. Along with that, we have our confusion matrix, which provides a detailed breakdown of true positives, true negatives, false positives, and false negatives, offering insights into the types of errors that the model makes. Two different architectures were trained, the DNN and LSTM DNN model, on the hybrid dataset. From these performance metrics, we can interpret that both DNN and LSTM DNN models showed similar performance across most metrics, if not better. But DNN model stood out for its lower computational complexity. DNN model's simplicity makes it more efficient to train and deploy. Given that it has achieved the same level of performance as LSTM, it is a better choice for real-time applications. Further, we have our receiver operating curve. The receiver, as you can see, the high value of AUC and our detailed confusion matrix analysis can confirm that our DNN model's ability to accurately distinguish between seismic and non-seismic events and minimizing positives, false positives, and negatives. In conclusion, research demonstrates that our DNN model is highly effective for seismic signal analysis, and it strikes a balance between performance and computational efficiency, making it an ideal choice for practical applications. The creation of our proposed and hybrid datasets provide a solid foundation for our work, ensuring that our models were trained on diverse and comprehensive data. As a result, we can confidently apply these models in real world scenarios to improve seismic event detection and reduce false alarms. And these are our references.